The next speaker is Julien Vanegue, and he will tell us about using bi-abductions to do program synthesis.
Can you hear me? Hello? Good. Excellent. Hello. Well, thanks for having me here. My name is Julien Vanegue. I'm heading the security research team at Bloomberg in New York City. And I've known Peter for the last few years. Particularly, Peter's support has been unparalleled in me continuing my research, and particularly in the last few months and a year or so, working with adversarial at the Imperial College. And so in my world, I care a lot about what happens when those pesky security exploits are actually trying to take advantage of your security vulnerabilities. And we see a lot of those vulnerabilities every month. We see those security bulletins coming up. And what really happens when one of those vulnerabilities come up? So people want to really try to fix as fast as they can. And there's so many of them that it's really hard to actually find a needle in a haystack. And so I must say, when Julien Vanegue invited me, I was very pleased. And after seeing the few titles of this track, I thought, oh, it's going to be Peter O'Hearn's roast. But as a matter of fact, it's going to be my roast after seeing everybody else talking. So why? And the way I want to start here is why incorrect logic matters. So obviously, we have more and more code. The software stack that we use in industry is becoming even more distributed. There's a lot of industry pressure to adopt tools that can actually be used by developers, things that can be part of the CI/CD, the continuous integration pipeline. And really, this is really large scale. So we're not talking about a few tens of lines or hundreds of lines of code. We're talking about millions of lines of code, tens of millions of lines of code. And really, that dictates the adoption of no false positive logic. You may have heard that term before. And Peter's contribution really has been to formalize this incorrectness logic in the last few years. It's something that has been very intuitive to security engineers and verification engineers in industry for a very long time. And really, incorrectness logic came and really captured that in a very succinct and pleasant and usable way. And another really advantage of incorrectness logic and its mechanism is that it takes a step to explain errors. In terms of, it's not just about, oh, you have an error and you don't have an error. It's also what it is that the error allows you to do as an attacker, or really as a initial condition, say, or an external condition. What kind of errors is going to be induced by those initial conditions? So this is really useful when you are in the industry because you always have to explain those vulnerabilities to developers. People don't want to fix things unless you really explain them what's going wrong and how they can fix it, of course. And so a bunch of new research questions actually stem from that. First of all, how can we prioritize bugs fixing? Because we have a lot of bugs, we have hundreds of bugs, thousands of bugs. Which bugs should we fix first? So this is a really good question, and we can use incorrectness logic reasoning for that because we care about those bug weaknesses, right? How can we actually prove the presence of a vulnerability rather than necessarily proving the absence of them? And so we want to be able to extend mechanisms available from incorrectness logic to this new word called exploitability, which is really, you give me a bug and I'm going to tell you whether that bug is an exploitable bug, is a security bug, or is just what I'm going to call a benign bug. And on top of that, can we generate the weakness automatically for that bug? So those are the research questions that will guide you throughout this talk. And so I've been thinking about that for quite a number of years, and after incorrectness logic came along, I really had this click, and I thought, oh, that's really what I need to work against. It's really a framework I really want to actually adopt for something I call adversarial logic, published at SAS a couple of years ago now, where I mixed incorrectness logic and the Dole-Viao model, which is originally adopted to study the security of cryptographic protocols, where you have this active attacker within the formalism, where you have, most of you know about the Alice and Bob protocols and all that, and Mallory come into place. So can we mix up program logic with a model that's typically used for cryptographic protocol verification? And that's where these kind of examples come into play. So let's play a number game for a second. I'm going to actually go through this example. On the left side, you have a target program. A target program is trying to really serve a client based on a specific credential that the client provide. And so it has a while loop, and it's just receiving a bunch of value into the variable credential at line 7. And it checks whether that credential you provided is equal to the secret. If so, there is no error, error code equals 0. Or if the credential was actually too big, error code will be 1. Or if the credential provided is too small, the error code is going to be 2. And if you provided the right credential, it will serve the client. Otherwise, it will just send you an error code, and whether 1 or 2. Obviously, there is a problem with this protocol, and the problem is that there is a side channel attack, or an information disclosure attack, one may say, where by a linear amount of attempt in number of bits of the secret, you can actually deduce the secret by having an adaptive attacker that overshot or maybe undershot, and then based on the number of a very small amount of attempts, you can actually recover the secret. As you can see, you have an active attacker in this logic, where on the right-hand side you have an adversarial program. And this adversarial program, what it tries to do is to really guess the value of the secret held in the target. So in this model here, of course, the adversary doesn't have access to the memory of the attacker, of the target. That would be too easy. But he tries to actually infer things about the adversary, about the program, based on its interaction with it. And the only primitive you have in adversarial logic to do that is read and write, which is basically sending and receiving messages. So as it turns out, and one additional characteristic of adversarial logic is that you are trying to satisfy an attacker contract. You're not trying to prove a code contract. You're trying to actually prove that a certain condition of the attacker is satisfiable. And that is translated by this the adversarial assert, where we're trying to find an execution and one execution where the return of this message from the target is 0, meaning that you get the secret properly. And so you're proving the presence of a vulnerability rather than proving the absence of them. All that is good and well. Unfortunately, the semantic of adversarial logic, as I proposed originally, is a little bit clumsy. First of all, it's using an interleaving semantic. Remember, you have this parallel composition between P and A, which is the program and the adversary, and you have to choose the specific interleavings that must be taken in order to actually reach those vulnerable conditions. Working with Azalea Wrap from Imperial, we were able to generalize this concept to a new logic we call Castle for concurrent adversarial separation logic. Not only this adds the ability to reason about pointers using the separation logic primitives, but also it uses relay guarantee that allows us to have modular proofs between the adversary and the target program. So similarly, here in this small example, you have on the left-hand side an adversary, on the right-hand side a target program, and the target program holds a secret. Unfortunately, there is a bug in this target program where it is doing a bound check if x is small or equal to 8. But as we all know, in C, the arrays are starting at index 0, and therefore if you index the array at index 8, then you will actually access what's after this array in memory. So that's another aspect of our work, which is not only it actually has this separating conjunction, but also it has this inner understanding of the layout of memory. Meaning, because you need to know that Z is just before W, which is itself just before the secret in memory, in order to actually perform this information disclosure. I'd like to call out some of that, the foundational work from Victor Lafayette, Matthew Parkinson, also Cecil by Rad, Burdin, Dreyer, and O'Hearn, and also what we published at Concur last year that generalized that and mix it up to provide an adversarial logic that's really able to reason about pointer as well as concurrency in a modular way. So what is next? So that's great. Adversarial logic and Castle, they work great at representing those exploits conditions. However, it still requires an adversarial program in order to actually reason about those vulnerabilities. And so in practice, you don't have this adversarial program. In practice, you have a piece of code, a program that has bugs, but you don't have the exploit. You want to know whether that exploit is feasible. Is it actually feasible to write an adversarial program that will try to take advantage of that vulnerability? And so can we synthesize this program? That's the next question we want to answer. And an idea is to combine bi-abduction and deductive program synthesis. So I'm going to talk about that a little bit today. Of course, I'm basing a lot of this work on the foundational work on bi-abduction by Calgano, Di Stefano, O'Hearn, Ong-Sek-Young, also work by Ishil Dilig and her collaborators on using bi-abduction to infer loop invariants. And also there is this paper from Philippa Gardner who, from my knowledge, actually used bi-abduction the first time around for program synthesis, in that case test synthesis in the JavaRT framework. So just quick recalls for, I'm sure everybody knows this way better than I do in this room. So what is abduction? Abduction is computing the missing part of a precondition, P, such as given the precondition, that missing part, you can prove the postcondition. It's a forward technique. And on top of that, you have bi-abduction. This bi-abduction really is, you can think of it as a little bit as a generalization of abduction, where not only you have to actually find this missing part, we call the anti-frame U in this case, but also you have to have a post-condition that's separable, where you have a Q and separately F, and where F is called the frame condition. And you can chain bi-abduction. Where, say, in this rule, for example, bi-abduction sequential, where you have a couple of assumptions here. You know that P1 goes to Q1 by executing C1, and P2 goes to Q2 by executing C2. Well, provided that Q1 and separately the anti-frame entail that P2 and separately the frame, you can actually know that P1 and separately U, C1 sequentially composed with C2 leads to Q2 and separately F. It's one of the rules that Calgano actually wrote in his paper. And there are a number of different rules like this. There's, for example, this BA with rule, which deals with parallelism and it can actually be used for concurrent program as well. So let's take back our small example and we'll simplify that a little bit. And this time around, we're not going to have this parallel execution composition. We are going to have an adversary for simplicity that calls into the program. And it calls into the program, the same program as we said was vulnerable. And we want to be able to infer what would be the adversarial condition for us to be able to exploit that program automatically. And so we pose the problem as such. What are the missing parts, U, the anti-frame, in the precondition of the program, and the frame condition in the post-condition, the frame part in the post-condition, so that we can actually reach those specific vulnerable points. And in this particular case, we'd like to be able to leak the secret. The secret is, say, V of S, the value of the secret, and we want, in this adversarial post-condition, to be returned that value of the secret. Also, conveniently, we can just pose the adversarial precondition as an empty set, just empty formula, that is. And so how can we actually use bi-abduction to actually start reasoning about synthesizing the program? As it turns out, you can certainly use the bi-abductive or bi-abduction algorithm that people came up with already. So there's no modification to what Calgano and others after him did, which is that you can really easily, just by using the vanilla bi-abduction algorithm, to actually come up with those anti-frame and frame, where just by actually computing the verification condition and combining that with an adversarial slicing of the pre and post condition, where you start with the goal of the adversary in the frame, and your goal is to actually infer the anti-frame, meaning that the adversarial input to the program. And it turns out that in this particular case, the adversarial input is x. If x equals 8, then we saw that we will actually index the array out of band. So you start by having the frame, putting the frame, saying the frame is actually the desired outcome for the adversary, and then coming back trying to infer the anti-frame based on the desired adversarial output. All that is good and well, but we haven't talked about program synthesis yet. So as a recall, program synthesis, you're giving P and Q, and you want to infer C. Say I have a pre and post condition. Is there a program, a C, that actually goes from the pre and to the post condition? In our setting, the synthesis is slightly more complicated, where we want to do adversarial synthesis, meaning that we want to infer an adversarial program that, when composed in parallel to the target program, will actually lead to the desired adversarial post condition. And so what we've done by using bi-abduction here is to separate that problem of actually synthesizing a parallel program to synthesizing a sequential program, which is obviously much more studied. And so our new problem really is to find out whether there is an adversarial program, CA, that goes from the empty precondition to the precondition of the program, and that precondition of the program, once executed, the program will lead to the postcondition of the program, QP, and that postcondition of the program, QP, will actually imply the desired adversarial postcondition. So by using bi-abduction, we reduced a concurrent program synthesis to just a regular sequential program synthesis, which is obviously much simpler. And so I'm not going to talk about deductive program synthesis for a very long time, but I would like to call out the excellent work from Nadia Polikarpova and Ilya Sergey, who published, in fact, program synthesis for heap programs. And for example, in this particular case, they have this small example for synthesizing a swap function that takes two parameters, x and y, and basically have x equal v, y equal w, and then ends up with x equal w and y equal v. And so, just like really briefly, how does that work? You have a bunch of rules, and the interesting rule here is the empty rule at the top, where you want to be able to finish by this empty rule. And on the right-hand side, the synthesis proof, they work bottom-up, where you start by the desired specification here. You're saying, oh, I have, for example, x points on value A and y points on value B, and I want to get 2 x points on value B and y points on value A. So I want to swap the two. I want to swap the two values, and I wonder what the program actually is to be able to do that. Well, just using those 4 rules, in fact, you can lift those specifications step by step. And at the end, once you've actually lifted all of those assumptions, you basically get to the point where your empty maps to empty and you're done. So it's really interesting. And this was enough to actually synthesize a bunch of heap programs. It sounds like this is really a framework that can be adopted out of the box for these kind of questions. And here, remember, we simplified the problem slightly because we started with a parallel composition of programs, an adversary and a target program. But then, for the sake of bi-abduction, I simplified and I said, oh, let's have the program actually call into the adversary. So I cheated a little bit. But if you want to keep the original setting, right, where the program is indeed in parallel with the adversary, you need new rules for this synthesis. And so I've been starting to think about some new rules for program synthesis, particularly those rules that can be used to synthesize parallel and concurrent programs. And so the rules potentially could actually look like that, where if you have you read bottom up again that rule, the power rule, say, you have a couple of different programs. So you have the context on the left here, and then you have the pure part of the precondition and the spatial part of the precondition, and for the left-hand side and the right-hand side. And you have the same for the post. So interestingly here, the star, as you can see, normally the star is actually inside only the spatial part of the specification, right? It's not for the pure and the spatial part. So here there is a slightly different use of star. So let's say that you actually have this synthesis problem, and you want to basically try to infer the parallel composition of the program C1 parallel C2. Well, you can quite trivially, of course, say, you know what, I have those two subproblems here where I know I just have to synthesize C1 that goes from P1 to Q1 and C2 that goes from P2 to Q2. And similarly, you can actually have a sequential rule that can do similar job. So because I'm running out of time, I'm not going to explain too much, but I'd like to thank you, Peter, for all the guidance and support and your unparalleled kindness in this research and your support that was really, really meaning a lot to me, and it still is. And with also your unparalleled sense of style. No, I said no roasting. And obviously, this is still work in progress and to be continued. Thank you so much for your attention.
So thank you very much. Do we have time for one question? Okay, yeah.
I'd like to ask you about the state of the art of program analysis for security. So normally you've got something like taint analysis, which is I make one call which takes me from say the internet to a bad place, like a database. But you've got these programs that make multiple calls. Is the state of the art missing the kind of exploits that you're talking about where you have like I think it was oscillating bit protocol?
Mm-hmm. Taint analysis is really good to analyze sequential programs, where you have a parser. Typically, the parser is trying to parse some binary, input and tries to lead to a structured in-memory representation. So when you have this kind of target, I think taint analysis is exactly what you need. When you come to concurrency or even like distributed architecture, where you have microservices and several microservices communicating and collaborating with one another to actually achieve a task, I think taint analysis is not what you need, because taint analysis is too strong. Where not every assumption can be taken, even though those microservices say are running in different machines. Typically, you have an entry point microservice, and then you have your production microservice. So, saying that everything is sent as input typically doesn't fly very well with developers. So yes, it's not there yet. Still the work to be done there.
Okay, so let's thank the speaker.